Everybody, welcome to Chapter 11 review. As always, to stay on some areas of focus, is not going to be a comprehensive review, but it's going to be enough for you to point you in a direction that you could definitely gain some knowledge for the exam. Chapter 10 and 11, they're huge chapters. Muscle chapters are always big. You have, in Chapter 11, we're going to be covering information regarding the physiology of the muscles, okay, different types, skeletal, smooth, and cardiac. So it's important for you to really get a handle on different types of mechanisms for each of those types of muscle fibers. And I'll go into a little more specifics for the exam as we get through this review. For chapter 10, which is going to be worked on next week, there's a lot of information. A lot of muscles, a lot of origin, a lot of insertions. I recommend flashcards if you could muster them up real quick. And you can look at them every day as you go through your material. So chapter 11 is mostly the physiology of muscle tissue. So let's go ahead and get started on the review and some areas that you should focus in on as you make your way through the material. So one of the topics you should cover is voluntary versus involuntary muscles. Obviously, skeletal muscles voluntary, cardiac and smooth are involuntary, but when it comes to those three different types of muscles, you should know why they're voluntary and why they're involuntary. Skeletal muscle obviously is under neurologic control or your neurologic control, whereas the cardiac and the smooth are going to be under sympathetic and parasympathetic control, something that you really don't have control over. That's why they're called involuntary muscles. So know the differences between voluntary versus involuntary, meaning why is skeletal muscle voluntary and why is cardiac and smooth involuntary. You should understand how the muscles are broken down to the epi, peri, and endomysiums. Okay, so basically the elastic components of the muscle itself. Where is the epimysium versus perimysium and endomysium, and know what they do, which each of them are responsible for. T-tubules, pretty specific right here. T-tubules, make sure you know where they're located and what's their function. What do they do? What do they transmit from the surface, from the sarcolemma down into the muscle fiber itself? Okay, make sure basically what this kind of tells you that you should know the anatomy, right, of a muscle fiber. They have T-tubules, and you should be familiar with what they do and what they and where they're located. Right, so if we look at action potentials, right, action potentials obviously are carried down T-tubules, but then what's the result of that? Where did the action potential come from? Where is it going? And what does it do when it reaches the end of its T-tubule? Right, at the end, at the terminal cisternae, right? This is a big one. This covers a lot of information in the chapter 11, the sliding filament theory and all its components, which means what? It means tropomyosin, troponin, your actin sites versus your myosin, myosin heads, excuse me, right? So you should understand how they all work together, how they fit together. Where does ATP play a role in this? How does the sliding filament theory work? As the myosin head attaches to the actin, but before that happens, what needs to occur? Tropomyosin needs to be moved out of the way in order to reveal the actin sites. Once tropomyosin is moved out of the way and the actin head or the myosin heads attached to the actin sites, then we get a contraction. Well, then how's that contraction broken? So once the contraction is broken is where ATP comes into play. And it kind of relates back to your assignment this week, your writing assignment this week of rigor mortis, right? So the sliding filament theory and rigor mortis kind of go hand in hand. Without XYZ, you get rigor mortis. And if you are alive, obviously you don't have rigor mortis unless you have an issue. So when it comes to the sliding filament theory, it's really important for you to know all the components, where they're located, how they work, and what they do to accomplish their job. Right? Every time the myosin head grabs onto the actin, we pull. It contracts that little muscle fiber. And then it's transmitted all the way down to the muscle belly, and then you get a whole origin to insertion contraction. This is another big one for chapter 11, the sarcomere. What is a sarcomere? Basically, you should know what the sarcomere is. Know all the zones, the I band, the H band, the Z discs, and the Z discs come together. Know what the sarcomere looks like before it contracts and then look at the sarcomere after it contracts. As those two Z discs come together, right, we start to narrow some of those bands. We start to change the look of that sarcomere because, remember, the dark areas of the sarcomere are the myosin and actin head, the myosin heads and the actin filaments getting together. And as they contract, the sliding filament theory contracts, you shorten the sarcomere. So I really want you to know what happens to those I bands, H bands, A band, Z discs, whatever. As those Z discs are brought together, I want you to know what the change is after contraction compared to what it looks like before it contracts. I know the textbook has some pretty good pictures of that, so you definitely should look at those pictures. When it comes to the T tubules, I think I have that coming up. Let's see, hold on. Yeah, here it is, right? Synaptic vesicles, pretty straightforward, pretty simple, located in the synaptic knob, right, of your neuromuscular junction. As that axon attaches to the top of your sarcolemma, it's going to release neurotransmitter, or it's going to at least bring that action potential, which we haven't gone over nerves yet, but the action potential down the nerves to the neuromuscular junction. It's going to release XYZ neurotransmitters, which they'll cross the synaptic cleft to interact with little receptors on the sarcolemma, thus causing a chain of reaction. Right? This is when it comes to nerve and muscle interaction, and all the way down to the sarcomere contracting, it's a cascade of events, and it all starts with the nerve. As it travels down the axon, synaptic node, or synaptic knob or node, the same thing. Synaptic knob is where the vesicles are located. All the vesicles will migrate to the neurolemma, which you'll learn in the next couple of weeks, and then the job is done. It takes place. It releases neurotransmitter, and we get eventually we get a muscle contraction. So when it comes to synaptic vesicles, it's important for you to realize where they're located and what's their function. All right, as I change my page here. Just a little slow. No problem. There we go. Muscle contraction. So when it comes to, now we're actually in the muscle contraction itself, be familiar with the different types of muscle contractions. Isokinetic versus isometric versus isotonic. Eccentric versus concentric, so I'll go over that later on in the review. You should be familiar with all those terms. And what does the muscle do during an isokinetic versus isotonic contraction or isometric? What's the muscle do during an eccentric contraction versus a concentric contraction? So be familiar with different types of contractions. Characteristics, kind of goes back to the first concept of voluntary versus involuntary characteristics of smooth muscle and cardiac muscle and skeletal muscle. Just know the different players within each of the types of muscles, right? What components do they have? Because when you look at a smooth muscle versus a skeletal muscle, there are going to be some components that are different because they contract differently. All right, they contract with different proteins, if you would. Like you'll see that when I go through the review a little bit further. But be familiar with the components. How does a skeletal muscle contract? Sarcomere. Well, does a smooth muscle and a cardiac muscle have a sarcomere? Something for you to investigate. The role of ATP, right? ATP, right, in contraction, which kind of relates to this one as well, the role of creatine kinase. When we look at muscle contraction, we look at different types of muscles, like your type 1 versus type 2 versus type 3, if you want to go that far, or your white fibers versus red fibers, and their role in producing energy and work, right? Those that are red have more myoglobin, which allows them to have more blood flow, more opportunity for nutrients, for glucose to make ATP. So you may look at long distance runners with those myoglobin or those red fibers versus a white fiber for the glycolytic type concept of a burst of energy and then you're out of gas, if you would, and you got to remake your ATPs. So where does the creatine kinase come into play? So be familiar with creatine kinase and how it helps to replenish ATP, as well as where's ATP in the muscle contraction. Go back to your sliding filament theory. That's where you're going to find ATP as well as how much ATP is found in each of the muscle fibers, white versus red, anaerobic versus aerobic, so forth and so on. So ATP is aerobic respiration, and we also have those concepts of these muscle fibers that you just see popped up on the board there. So muscle fiber types, slow versus fast, red versus white fibers, type 1, 2, and 3. You have slow oxidative, fast glycolytic, fast oxidative glycolytic. That's my little film is in the way there, but know the physiology of each. Know that myoglobin, if you have a red slow twitch, which they kind of go together, red slow twitch versus a white fast twitch, right? The red slow twitch contain more myoglobin and glycogen, because red means blood, if you would, and that means you have more glycogen, more opportunity for energy to give yourself a nice long run. Whereas if you're a white fast twitch fiber, you don't have much myoglobin. That's why you're white, if you want to look at it from that standpoint. What else can I say before I move on? Myoglobin. I guess myoglobin is a key word. You should know myoglobin, what it means, and how it relates to the type of muscle fibers you see up on the board here. When it comes to the sarcomere, again, be sure to understand, again, when it contracts, what's the change of the sarcomere. I'm sorry for jumping around, but as I go through my notes, we're going to go into that concept there. The role of calmodium in smooth muscle, this kind of goes back to that one idea I'm asking you to look into, is what's the difference between smooth versus skeletal versus cardiac? What are the players, if you would, in each of those muscle types? Because we know smooth muscle contracts differently, and hence the word calmodium, right? So make sure you look at the different components of skeletal versus smooth versus cardiac. Organize yourself with those concepts so that you know that, hey, if a question comes up that has the word calmodium in it, obviously it's going to be smooth muscle, but know what it does and how does it differ from skeletal muscle. When it comes to creatine phosphate, going back, okay, remember it's a catalyst that transfers phosphate from your creatine phosphate to your adenosine diphosphate. As our ATP converts to ADP, in order for you to convert that muscle, in order for you to contract that myosin head on the actin filament, in order for us to get that ATP back to its original form of ATP, because now it's ADP, your creatine phosphate helps to jump in and take care of that. So I'm kind of jumping around, but you get the picture. Gap junctions. What are gap junctions? Know where they're located. Know what they do. When it comes to ATP, again, I can't get off ATP, sorry. Make sure you know what ATPase, right? The enzyme that breaks down ATP. Make sure you know where it's at, how it works, and what it does. Right? Pretty much everything, right? Gap junctions. Motor units. Okay, motor units are the way a nerve, where like one nerve will control an X amount of muscle fibers, right? So if you have fine control, that means you have one nerve maybe controlling such the eyes and the muscles of the eye. In order to have that fine tracking control of muscles in the eye, you need to have one nerve that's going to innervate, say, 10 muscle fibers, as opposed to one nerve innervating 1,000 muscle fibers in your quadricep muscle in your leg, because you don't need fine motor control. So one nerve per the number of fibers equals a motor unit. The less fibers that are controlled by one nerve, the more fine control you have. The more muscle fibers controlled by one nerve, the more gross movement you have, right? The lack of control. Gap junctions, jumping around, make sure you know they're in the visceral muscles. Okay, the characteristic of visceral muscles. This is an interesting concept, the length-tension relationship. The length-tension relationship has that graph that's in your chart. It's in your textbook. And the length-tension relationship refers to the sarcomere. What's the sarcomere doing before it contracts? The longer you stretch a sarcomere before you contract it, the less force you have to generate. As you stretch a muscle, you're stretching sarcomeres, which means less myosin heads will be in relationship to the actin above it. The less heads that attach, the less force that can be generated. As you contract a muscle, for example, the shorter the sarcomere, and which then at some point you cannot contract that sarcomere again because there's less space for myosin heads to attach to actin because they're all taken up. So you do decrease a force of contraction again, or there. Once you contract a sarcomere, you can't contract it again because it's not enough, there's no more room. Everybody's used up. So the length tension relationship means that at some point when the sarcomere is in normal position, neutral position, not stretched and not contracted before it's contracted, when it's in normal position, you generate a maximum force because you have the maximum number of myosin heads attaching to the maximum number of actin sites. Example, you bend over to pick up a block of wood off the floor and your low back muscles are already stretched. Since they're already stretched, that means your sarcomeres in those muscles are stretched to their limit, which means they don't have enough heads to attach to enough actin. So you go to contract, and then if you're weaker in a way, then you're going to pull that muscle or you're going to hurt your back because the sarcomeres are too stretched. They couldn't take that force of picking up whatever it is off the floor, and now there's no force of contraction because the sarcomere is stretched before it was used. So check out that chart, understand the length-tension relationship, and it kind of explains it pretty good. Neurotransmitters, the site where they're located, what are they? Acetylcholine, there's other ones. And what do they do and their function? Go back to the neuromuscular junction concept of the synaptic knob and the vesicles, and that kind of gets you started on the neurotransmitter area as well. Action potentials. Action potentials are and the activation of muscle fibers. Basically, where does it start? How is an action potential created? Now, we didn't go over action potentials per se yet. It's more of a nervous system idea, but we do cover this in the neuromuscular junction area. Okay, in order for a muscle to contract, you need to have an action potential. Where does it come from? What propagates it? And where does it start from? I guess I said that right. So when you think about action potentials and you think about activating a muscle fiber, you're looking at different parts of the muscle fiber, okay, such as the sarcolemma, transverse tubules, the terminal cisternae, calcium. The list goes on. So as long as you know the parts of a muscle fiber, then you can put them all together and see how they contract. Resting membrane potential and the role of sodium and potassium in this resting membrane potential. Okay, resting membrane potential is the potential of a cell membrane, which is the comparison of the number of negative and positively charged ions outside the cell versus the number of positively and negatively charged ions on the inside the cell. The difference between those positive and negatives on the inside and outside of a muscle fiber, of a muscle cell wall, determines a potential for energy, potential for electricity, potential for work. The resting membrane potential of a muscle cell is negative 90. Okay, negative 90 millivolts. You should write that down, right? Just in case it's not in the textbook, I'm testing it on it anyway. Resting membrane potential of a skeletal muscle, which is a cell, skeletal fiber, skeletal muscle, skeletal cell, all the same things. The resting membrane potential is a negative 90 millivolts. It's that resting membrane potential, it's the change of that negativity to a positive over time that creates an action potential. Okay, so be familiar with action potential and how it relates to this resting membrane potential of negative 90 degrees, negative 90 millivolts, sorry. Right, so an action potential, in an action potential, the sodium voltage regulated gates open first, followed by the potassium voltage regulated gates opening. Sodium opens first, potassium opens second. Okay, so in an action potential, the sodium voltage regulated gates open first, followed by the potassium voltage regulated gates opening. Sodium first, potassium second creates an action potential. And we'll definitely delve into this much, much more in the next units after this. After 10, we go into the nervous system. So that's just a quick overview of that information. Be familiar with that. ATP again, coming back to that, is just again, make sure you know the power stroke or ATP and the sliding filament theory. There's going to be some scenarios on there such as, hey, if I run long distances, I'm going to have more red fibers than white fibers. So it's kind of like just know your red and white fibers and all those different muscle fibers that we talked about before, and your ability to put that into real world concepts. For example, movement of your fingers are controlled largely by fast glycolytic fibers with small muscle units, right? So now you're incorporating two things, right? Your fingers have fine movement, so you know it's going to have a small motor unit, which means one nerve innervating a couple of fibers in the forearm and the hand, because I need dexterity. But they're also fast glycolytic fibers, which means they'll fatigue much faster than, say, a larger muscle such as your quads, based on the fact that they are smaller muscles, they're white fibers, they are fast glycolytic, and they're small motor units. So put that together. So put all the concepts together, such as type 2 and slow oxidative muscle fibers. Aerobic respiration. For example, you're eating, you prefer white meat over red meat in a turkey dinner. Which of the following characteristics would not correctly describe the fibers in white meat? Well, you know that white fibers of any animal or human doesn't have aerobic respiration because it's a fast glycolytic system, right? It's for speed, bursts, and energy, and that's it. It's not long distance. You don't have the myoglobin to create the red tissue that you would for that type of muscle fiber. So most of the time, a white fiber is going to will not have aerobic respiration. Oxygen debt, make sure you know what that definition means. And then going back to our concepts here, concentric contraction versus eccentric contractions, which goes to isokinetic, isometric, and isotonic contractions, kind of what I said earlier in this review. Be familiar with that. There are a lot of questions on the sarcomere. There's a lot of questions on the relationship of muscle fibers, and there's a lot of questions on ATP. A couple questions on the on the neurotransmitters and action potential, and that should pretty much wrap up the review for the course. These next two chapters are going to be probably the most you're going to have to really get into the material and understand it. If you have any questions, concerns, or comments, please email me. I'm here to help. And of course, this review will be posted soon, as well as the review for Unit 10, for Chapter 10 will be posted as well soon. All right, take care, and I'll talk to you later.